Okay, welcome everyone to the Sustainable Buildings Canada research presentation event, Community Energy for Multi-Unit Residential Buildings. I'd like to introduce Mike Singleton, the Executive Director of SBC, to say a few words.
Thanks, Adam, and good evening, everyone. Thank you so much for joining us on a beautiful Thursday evening at 6 o'clock, and we've got a lot of registrants, which is awesome. And I was just joking with our presentation team here. I think we've got more people signed on to a webinar than we ever had come to one of our live meetings, where we featured wine, beer, and some food. So this is kind of interesting. It must be a pandemic or something happening. But thank you, everybody, for joining us tonight. I'd like to thank our speakers. We have 6 wonderful speakers. You'll hear about them in a minute. Thanks to Adam Jones from SBC for putting this on for us. He's our technical go-to person. So thank you, Adam. So tonight we're going to be hearing about some of the aspects of community energy. So every year, SBC undertakes some research efforts, and we reach out to subject matter experts and consultants in the sectors and so on. And as part of that activity, they undertake research, which we publish as white papers. Those are on our website. And then we ask them to do a presentation. And ordinarily those presentations are live, but tonight we're going with the web-based approach, obviously. So I'd like to thank all of our research team, our 6 presenters this evening. We're going to hear some of the theory behind community energy, and then we're going to have some practical applications. So enjoy the evening. Thank you again. There is time for questions at the end, and Adam will walk you through that process. And otherwise, I'll turn it back to Adam. So thank you again.
Okay, thank you, Mike. All right, well, let's start with the agenda. So after the introductions, we're going to start with some research by Jenny McMinn and Michael Musa at Urban Equation on geothermal for multi-unit residential buildings. And then following that presentation, we will lead into Diego Mandelbaum of Creative Energy, his research on modern district energy systems in Canada, where we'll hear a little bit about some case studies of projects that are happening. And then we'll wrap up with Bob Bache, Vito Casola, and Akil Zaidi, who will discuss their research, combined heat and power for new Part 3 MURBs. And that's actually the short version of that title. And then we'll follow up with the Q&A. So if everyone can hold their questions till the end, but in this case, feel free to type your questions into the question box at any time. Well, we're going to save them up until the very end. And then we'll have close to an hour for questions at the end. So a little bit of housekeeping before we proceed is the Q&A session will take place following all presentations, and a recording of this entire webinar or presentation will be available on our YouTube channel. So we'll send out an email following this with the links to the YouTube channel and the link to sbcanada.org, where you will find the research papers themselves, so you can delve into this in greater detail. Now, to introduce the topic, I think one of the most interesting developments in the building sector in recent years is this trend of on-site energy generation and energy storage. And I say energy storage when most people think of batteries, but geothermal is effectively an energy storage system, and we'll hear more about that from Jenny and Michael. So these systems are being installed in all types of buildings, but for this evening, we're going to talk specifically about how they can apply to the multi-unit residential building sector. Sustainable Buildings Canada has supported this research with the aim of contributing to a better understanding of the technical and procedural challenges which may be preventing more widespread of these systems, and in particular because they have such a potential to provide both improved resiliency and reliability at the building scale, as well as contributing to a greater, more sustainable energy grid throughout the province and the country. To be frank, it's not just Ontario that needs to improve its energy outlook. So About the title, community energy is often a term that's applied to more residential. So it's usually used in the planning field to describe energy consumption and emissions from residential areas within a municipality. So new developments are required in many places to submit community energy plans describing the anticipated energy demand and the associated emissions for a new subdivision, for example. While municipalities have been pushing for and accounting for their emissions and trying to reduce them, well, those are the corporate emissions, they're beginning to turn their eye more toward these community energy issues and try to find ways to drive that down. That said, a single large multi-unit residential building can represent the equivalent of many hundreds of single-family homes. So it's imperative that we find a way to make these buildings have the most sustainable energy processes possible. So allow me to introduce our first presenters, Jenny McMinn and Michael Musa from Urban Equation. Whenever you're ready, please proceed.
Thanks so much, Adam, and thank you to Sustainable Buildings Canada for your interest in the topic. We're very happy to be here and nice to see so many folks out tonight. I do think someone's mic is not muted. Mike, I think that might be you. I just keep seeing the green square there, so oh, I'll keep going either way. So I think Michael and I are here tonight. I'm here co-presenting with, sorry, Adam, I don't seem to have control. You could advance the next slide. Thank you so much. Myself and Michael Musa are here tonight. We both work with Urban Equation. Next slide, please. Urban Equation is a consulting practice. We're part of a group of companies that's comprised of both us and the consulting work that we do, and also a private development entity called Windmill Developments. Windmill Developments was initiated first about 15 years ago, leading massive change projects like Dockside Green, trying all kinds of different technologies towards a true sustainable community development, inclusive of multi-unit residential. Since then, Urban Equation has been brought online to help share that knowledge and try to assist the larger development community in realizing their sustainability aspirations. So we can just flip to the next slide, Adam. Ooh. Okay, sorry for the technology glitches here. And the next one. I apologize, I'll just pause here for a quick second. I did want to recognize that, or as Adam had mentioned, we prepared a white paper that looked at geothermal and its application in multi-unit residential buildings in particular. We had a number of fantastic contributors that assisted us in our research. If you could just quickly go back to that slide, I just want to make sure that everybody is acknowledged who provided input. We tried to get a mixed bag of expertise, including both energy expertise from EQ Building Performance. On the supplier side, lots of great input from Diverso and Subterra and GeoSource, and also, of course, spoke with a number of developers as well. So thanks to all those who contributed to the report. If you could just advance 2 slides, and I'll hand over to Michael.
All right, thanks, Jenny. So I'll start by identifying one of the challenges our industry is trying to address, which is reducing building sector greenhouse gas emissions. These building sector emissions vary from province to province, where some province emissions are dominated by electricity use and others by natural gas combustion. This is because provinces such as Quebec, Ontario, and BC use low carbon sources to generate electricity, resulting in a higher relative impact from natural gas on greenhouse gas emissions. For multi-unit residential buildings, which are often called MURBs, and you'll probably natural gas use for space heating represents the highest energy end use for these buildings. This is a challenge, but it also presents an opportunity for greenhouse gas emission reductions, particularly in provinces where electricity generation is low carbon. Next slide, please. So the opportunity here, sorry, Adam, if you could go to the next slide. Thank you. So the opportunity here is shifting away from using natural gas as an energy source for MURB buildings. One way to do that is by using a geoexchange system, which is commonly referred to as geothermal or ground source heat pumps. The key attribute to geothermal is using the finger quotes free energy from the Earth's constant temperature to provide heating and cooling to a building. So essentially exchanging heat with the ground. When a MURB uses geothermal, it has the potential to replace natural gas use for heating entirely, using only a small amount of electricity to convert the earth energy. While the primary heating and cooling energy source switches from natural gas to electricity, the efficiency of a geothermal system typically balances out and saves on overall energy costs. Next slide, please, Adam. So in addition to replacing natural gas as an energy source and reducing those related greenhouse gas emissions, geothermal can also reduce the total energy consumption of a development. We completed an analysis of a MURB located in Ontario to determine the impacts of geothermal on both energy and greenhouse gas emissions. Just to note that the majority of our data presented today is Ontario focused, and this building is in Ontario. So to analyze the potential energy savings between a typical natural gas-fired two-pipe fan coil unit system and a geothermal system, we isolated the space heating and cooling design of the building and kept all other characteristics constant. The results, which are shown here, are a 33% total energy use savings when using a geothermal heat pump system and a 47% decrease in greenhouse gas emissions. This also resulted in an annual operating energy cost savings of 10% when normalized by suite. The largest decrease in energy use between the two systems is found in space heating energy, which reduced by 93%, and it's the navy blue bar in the figure on the left. This resulted in a significant decrease in the related greenhouse gas emissions due to the reduction in natural gas consumption. As predicted, the electricity use in the geothermal case increases due to the use of heat pumps to provide the in-suite heating and cooling at the desired temperature. Next slide, please, Adam. So the energy and carbon benefits of geothermal have been understood for some time, yet there's been a relatively slow uptake in the MURB sector. According to a study which reviewed the energy models of 95 MURBs in the Toronto market, the most popular HVAC system in the last 5 years are natural gas-fired fan coil unit systems. None of the 95 buildings used a geothermal system. While this is only a snapshot of the Toronto market, geothermal is only in the last few years gaining popularity. Many new geothermal providers have entered the market in the last couple of years, and there's a growing interest from MURB developers, where most are now at least exploring the potential. So our presentation aims to demonstrate not only the carbon benefits that I've highlighted here, but also address the perceived barriers of implementing these systems. And from there, I'll hand it back over to Jenny.
Thank you, Michael. Next slide, please, Adam. So as Michael mentioned, one of the areas of interest for us in looking at the study was, we did kind of the basic technical analysis to understand what the potential and both the potential as well as the realized performance of MURBs connected to geothermal buildings. But what struck us as really interesting is how the development community has responded and this relatively slow uptake of these systems, as it's not really new technology. It's just that it's not really being adopted at a rapid pace. And so, anecdotally, I recall about maybe 5 years ago, working with a developer here in Toronto, we went through the rigorous technical and financial business analysis, and I was so excited that we made the case as a very low carbon building. connecting to a community geothermal system in this case, showed a positive IRR, and I was really pumped going into the meeting, and then the developer just said, that's a really great analysis, we're not interested. And I was like flabbergasted. I'm thinking, but we've shown that it works financially, and we've shown the technical viability. And what I realized leaving that meeting is that, well, there's lots of different takeaways there, but I think that obviously we operate in a fairly conservative sector, and that there are still many barriers to implementation. And so one of the main objectives of our paper was really thinking about it from the owner's perspective, and how can we start to unpack these barriers and just provide some more information. Not suggesting that geothermal is the right solution for every MURB by any means, but there are a number of, I think, barriers to help dismantle. So we'll aim to talk through those in the next section. Adam, next slide, please. So one of the first barriers, which is a fair one, depending on how the multi-unit residential building is structured, is a higher upfront cost. And so the drilling of boreholes to create a geothermal system is typically more capitally intensive than a comparable alternative mechanical system. That said, geothermal can afford a reasonable payback term of, and I think we'll get into that in a little bit more detail further on, of about 5 to 7 years. And what's interesting in the last few years is that there are some different options for developers, particularly interesting to condominium developers, to partner up with a third party who will come in, design, build, own, and operate the system as an energy service provider, which is mutually beneficial in that the developer is reducing their own capital costs typically to do that. And the benefit of the system, i.e. the energy savings over time and the carbon gains over time, better align with a utility-like model, someone who will come in and run the business for 30 years and work with the condo board in a customer situation. And so I think there are a couple of different plays here for the private condo developers to consider alternative means of moving towards these lower carbon systems. Next slide, please. So I think I've probably already stolen the thunder from some of the key points from this side. In terms of the potential for cost savings, in addition to the obvious of, especially when partnering with a third party, of taking the crux of the capital cost of drilling the wells onto someone else's balance sheet, there are some other real financial gains as well, which can often include the freeing up of roof area, possibly the reduction in the mechanical plant size, the eligibility for incentives, and also potentially a reduction in structural cost at the roof level. Particularly interesting in the Toronto market and the Vancouver market as well, is as codes are stepping up and asking for more, we're seeing condo developers pay more attention to alternative systems like geothermal. In terms of the actual cost of the system, the geothermal system itself, there are a number of factors, including location of bedrock, how many boreholes are required, and what the potential for energy balance over the course of the year will be, as well as any underground unanticipated conditions like aquifers. So next slide, please, Adam. So this is just another way of looking at the potential financial benefits, and this is really considering it mostly from a condo developer, so not even really a longer hold rental situation. And just as I mentioned, this is one sample financial analysis that we looked at. These are dollars per square foot costs, which even with the reduction, so there's a reduction in the mechanical room, as I mentioned, the reduction of mechanical equipment, particularly boilers, chillers. There is often a currency exchange between a developer and a third-party energy provider, which is called a connection charge. And that is usually to help balance out the cost and make sure that, that both sides are in fact making money while maintaining market rates to the end user. In this particular case, we were seeing a potential of savings of about $1.50 per square foot while still hitting these higher levels of carbon efficiency. Next slide, please. One of the other real barriers to geothermal application, in particular in that some of the earliest precedents were set up where I think either intentionally or not, developers were really setting up to save as much upfront capital as possible and push the burden onto the condo board, incurring higher fees. And what we're seeing now as a means of ratifying that is that, so what we're seeing is that so long as the energy agreements are set up well in advance, clearly communicated as early as the sales cycle with prospective buyers, and that the energy rates are set up in no higher than market rate and ideally even a little bit lower, that generally that early socialization helps to mitigate any of the perceived barriers to entry. And in some instances, we're slowly starting to see that there is a potential benefit as well in the sales cycle to be communicating these lower carbon applications. The one thing to note, and this may be obvious, is that the arrangement with the energy service provider does need to consider, particularly for mixed use, how that structure will be set up. It is, of course, more complicated in a broad mixed use facility to set that the legalese, but there are many good precedents now in the Toronto market. Next slide, please. Geothermal is still new to many developers, and so I won't read line by line what the implications are, but there are some changes that are required in terms of the design process, the financial terms process, the legalese that are required to set up, in particular if working with a third-party developer. In general, most HVAC systems connect fairly well to geothermal systems. Sometimes there's an opportunity to connect or at least preheat for domestic hot water. Many developers we're seeing in recent years are exploring geothermal actually as a means of getting within their zoning heights, which can be an advantage for some projects. And then also just the coordination with the mechanical room and sizing, and really realizing those benefits as early on as possible. Next slide, please. We did map out a fairly simplistic but 9-step process of how and when to do modeling, how and when to engage with the market. And in general, I think for projects that are looking into low energy, low carbon buildings, really engaging external providers early on is quite helpful. And really just testing the viability of geothermal or other systems. Otherwise, I think I'll just keep going. Next slide, please. So there's a couple of other key barriers. I think Michael's adequately spoken to this one out of the gate. Obviously, in the Ontario market, natural gas is cheaper per unit than an equivalent unit of electricity, as Michael had pointed out, and we've seen on many projects. Because of the potential efficiency that geothermal realizes, we're seeing that the cost to the end user can be at, or as Michael had pointed out, about 10% lower than a market rate building using natural gas. Next slide, please. A couple of other key barriers. We talked a little bit about it. Geothermal is not obviously applicable for all projects. Soil types and ground conditions are obviously a huge consideration. We've heard from some developers some concern around additional soft cost premiums. We're not really typically seeing a need for separate specialized mechanical engineers, particularly if you are engaging with a third party. Lots of very experienced folks to work with in that regard. And in terms of the life cycle expectancy in general, the geothermal system working with heat pumps has a fairly long life expectancy of between 20 and 25 years. Backup heating and cooling obviously needs to be considered on a building by building basis. And there's lots of creative ways of providing top up heating within a building without actually adding additional equipment. There's a couple of good precedents that were able to leverage excess capacity from their domestic hot water boilers to be able to provide any top up or backup needed. Though certainly in some of the earlier precedents, we were seeing full redundancy as people are just getting to know what's possible, but should be considered early on, and I think not assumed as a foregone conclusion. Next slide, please. So I think just to sum up, we are seeing a lot more movement. There are more suppliers in the market, and so there's opportunity for competitive pricing. And we do see that geothermal is a useful system that can offer low carbon and in many cases lower upfront costs as well as operational costs over time. And we have a full paper for those of you that want to read a little deeper, and I believe that's posted now on the Sustainable Buildings Canada website. So thank you.
Okay, thank you, Jenny and Michael. So next up on our agenda is Diego Mandelbaum from Creative Energy. Okay, Diego, whenever you're ready.
Can you hear me okay?
I can hear you.
Okay, so I went one too far. There we are. There, I've learned how to control this. So thanks for having me. I'm a little bit of an exception today. I've not written any research papers or published them or any white papers. I am here to talk a little bit about district energy and what we're seeing in Canada. And this is really analysis that we're doing as an energy developer from both British Columbia and Ontario. And so sharing a little bit about that. It's kind of interesting. I'm in the middle between a presentation about geothermal and CHP. And the two case studies I'm going to show, one has geothermal and one has CHP. So I was a little bit explicit about that. And I quite enjoyed Jenny's presentation. I would say probably 95% of that I agree with, and I will be mirroring in some of what I talk about. And there's a little bit there that I see we've seen a little bit differently, but I think that's what makes good conversation. And see if I can go to the next slide. Yes. Okay, so in the next 20 minutes, give or take, I'm going to be doing a really quick introduction about who I am and who the heck we are. District energy basics, kind of the 101, though I've been led to understand there's a very sophisticated audience, so it sounds like I can skip through that one pretty quickly. Then spend a bit more time on modern district energy systems, which I think is more interesting. A couple case studies, and then the questions and discussion will actually be at the end of all the presentations. A lot of information to cover, and so that picture is a bit of a play on words to be ready to drink from a fire hose. And maybe just before I give a quick background about who we are and what we do, a little bit about myself. I'm a mechanical engineer by background. I spent about a decade in the consulting world where I really fell into central plants and district energy design, started working for one of the bigger district energy developers, and they got tired of paying my fees, I think, and brought me on board. And then I moved out to Toronto back in September to open up our operations here and lead some of the growth for the company. So far, it's been a good experience. And about us, we are pure and simple, we're a district energy company. Our background goes back to 1968. We were the first district energy company in British Columbia and one of the largest ones today in North America. And we've been around for over 50 years, have about 250 connected customers in our downtown Vancouver plant. And we're now actively in the development world purely for district energy as a design, build, own, operate, maintain type of entity. We are in it for the long run. A little bit about our history. This is kind of interesting. Unfortunately, one of the case studies I did not show is a redevelopment in downtown because of some confidentiality. But back, people may not know this, in the 1960s, Vancouver had all sorts of pollution issues. And so a group of engineers came together and said, we have a great idea. Why don't we set up a natural gas steam plant and connect all the buildings to it and start eliminating fuel, oil, and coal furnaces at every building. And back in the 60s, natural gas was sort of the sustainable fuel of the future. And it's ironic where today is the company spending a lot of money to decarbonize our downtown Vancouver plant and add some low carbon capacity. But in 1968, essentially they connected up to the first building, sold their first BTUs of steam, and it grew from one building to 210 buildings over about 50 years with about 15 kilometers of piping. And then in 2014, there's a big shift in the company to do two things. One is decarbonize the downtown Vancouver plant, which heats most of downtown Vancouver. But two is to go across North America and hopefully broader after that and develop brand new systems and get them off the ground and really focus on low carbon, innovative type systems. And so today, that's really where we're at. We're pretty happy to say we have our first construction project here in Smurfit Village, which I'll talk a little bit about later. And we have about another, I don't know, 12, 13 projects in development, anywhere between design, feasibility, construction, and early stage operations. Just to show a little bit about our downtown network, that's the infrastructure we have downtown right now. And that fancy looking building by the stadium, that's what the redevelopment of our plant will look like. It's actually a tower over top. Our current plant, it looks very, very ugly, and I would never show that to a big group of people, but that's what it will look like. And then some of the projects that we're involved in, and we'll be talking about two of these, but it's going across the board. We're doing a district cooling system in Vancouver, which the long-term plan is to recover the waste heat and actually sell that to the city of Vancouver because they have the district heating system there. A little node for Vancouver House, which is one of the more iconic buildings being developed in Vancouver. Ridge Village, as I mentioned, which is a CHP microgrid and district energy project. The, excuse me, our redevelopment downtown Vancouver. Oak Ridge, which is, I believe, one of the largest geothermal projects that's getting built in Canada right now, if not the largest, probably top 5 or so. And then one that I won't talk about today because of time, but it's really interesting. It's a smaller project for us in the bottom right. That's Horseshoe Bay. It's 7 small buildings, but what we're doing there is actually submerging 2 very, very large heat exchangers into the floor of the Pacific Ocean, anchoring it to the ground, running plastic piping through the seabed, tying it to an array of heat pumps in our central plant that's below Parkade, and heating 95% of the thermal energy with ocean exchange. So very little gas, no cooling towers. That's really a very interesting project for us from a technology perspective. And moving on to the basics. So what is district energy? Kind of the 101, and this is probably repeat for most people here. So I apologize if this part is just that, but I think it's important to note. And in short, it's a really simple concept. It's centralizing the generation and distribution of thermal energy from a group of buildings into one central location. And the reason we're seeing this is really it provides an economy of scale that is really competitive, particularly as we're moving into a low carbon era. What we see in our business cases is that when there's a low carbon or renewable component and there's scale, we can get levelized costs of energies that are significantly lower at scale at a neighborhoods kind of area than you can at the individual building scale. And then the other big benefits actually align quite a bit with some of what Jenny was talking about, that we're able to reduce a bunch of floor space, take things off of the roof, and fundamentally help developers or our counterparties avoid capital costs, because we would develop our plants and then you don't have to be putting in cooling towers and heat pumps and boilers at every single building. And even with the geoexchange application, you wouldn't necessarily have to put those at every building. You can centralize that and then you simply connect. One of the really interesting things too is that I like as a mechanical engineer is the ability to share energy among different buildings. A little bit of an anecdote here as a side note. In British Columbia, there's the University of British Columbia Okanagan campus. They have a geoexchange district energy system. They have an underground aquifer that they reject or supply or take heat out of. And then they have an ambient loop that connects all their major campuses. But 60% of the year, they actually don't have to touch their aquifer because of the different load profiles across the campuses. One building heats the other and one building cools the other. And so I thought that was quite remarkable, and that's something that you really get to unlock from a district energy or community energy perspective, which we're seeing more and more as we're moving into the more modern type of systems. The basics from district energy, and I think this applies to virtually any system, and I'm sure there's some exception out there, but it really comes down to 3 main components. On the left there, we have the energy center. You'll hear this be referred by many different names: a central utility plant, energy center, thermal heating plant, you name it, lots of different things there. But that is really where the generation equipment goes, whether that's a boiler or generator or CHP machine, heat pumps, cooling towers, so on and so forth. And what's probably worth noting here is you can, and I've got another slide to show this, but you don't have to hide them and they don't have to be ugly. There are things you can do to actually make them quite nice. And what you see on the left there, that's actually the City of Vancouver owned Southeast Falls Creek Neighborhood Energy Utility. What they do there, there's a large sewer main that runs underneath that. They do a sewer exchange where they essentially extract heat from the sewer, use that, put it through a heat pump. They then lift up temperature of hot water and serve about 5 million square feet of development from that. And it's actually built right underneath the Cambie Street Bridge, which is one of the main arteries that goes into Vancouver. And what they've done there for the boiler flues, they actually did it into an architectural design that's shaped like a hand, and illuminates the smoke at night so that any car that's driving through there at night actually gets to see this architectural feature, although 95% of the people probably don't know what it is. The second main component is the distribution piping system, or what we like to call DPS for short. And it's really simple. These are pipes that move the energy from the energy center to all of the connected buildings. What we'll typically see is 2 pipe systems, 4 pipe systems, or 6 pipe systems, though I will say the 6 pipe systems get energy modeled really well and never end up coming through on the economics. So we're seeing quite commonly 2 or 4 pipe systems, as well as some 2 pipe ambient systems, which is another conversation altogether. But these are really just simple pipes that can be put directly underground, under city streets, under private roads, or when there's a shared parquet podium, it's always more affordable if you can do that. And then the last component of district energy is what we like to call energy transfer stations. And that's just a fancy engineering term for saying heat exchangers. These are really small heat exchangers that are at every connected building. And this is the demarcation point between what would be the district system and the building system. And they take up typically about anywhere from 10 to 50 square meters or so. So significantly less space than what a boiler room or chiller room in a building would take. Sorry, it's a little too far. There we are. And so this is my pitch. I try to get this into every presentation I ever give, just to show that you can do some really interesting things from an urban placemaking perspective and architectural perspective. One of the questions that commonly comes up is, what will you see? Is this going to be ugly? Is this going to hurt my saleability? And what we're seeing is that in most cases, you don't know that there's a district energy system there because it'll be hidden below grade somewhere. For example, we're doing Smurfit Village right now, and our central utility plant will be in parquet levels P3 and P4, and nobody would ever know it's there. But we're starting to see a trend where it's starting to be celebrated, particularly as I think as a society we're becoming more aware of the global climate crisis that we have. And people are starting to be proud of their thermal infrastructure, energy infrastructure, particularly when it's using some interesting technologies and doing some good things for the environment. And so just a quick snapshot going left to right, I think I mentioned the Vancouver SEFC NEU already. But I think probably the most famous example in the middle there is Copenhagen's Copenhill, which is a very, very large waste to energy system that produces district heating and also produces electricity and has a ski hill over top. So this is orders of magnitude larger than most of the things we would see in Canada, or I would say probably in the States as well. But I think Europe is one of the places, particularly Copenhagen, who has really adopted district heating. I think 97% of their heating comes through district systems. Moving to the right a little bit, what you'll see here is actually the redevelopment of our downtown Vancouver plant. Anybody who's familiar with Vancouver, this is right beside the BC Place Stadium. And what's happening, there will be a kind of an S-shaped Class 8 office tower that's getting built above, that's being designed by the Björk Engels group. And our district energy plant will be, for the most part, in the bottom of that, and there will be a glass facade all around the pedestrian level with some exposed piping. And it's intended to actually be a demonstration piece and part of the public realm there to celebrate the city of Vancouver's energy backbone. And then as you move to the right, some biomass examples as well of what can be done coming from Germany and from Sweden. Moving away from aesthetics and a little bit more to the need or the drivers as to why we care about this. And there's really 3 main reasons for the most part why we see district energy and why we're seeing a real resurrection of district energy, particularly in North America. I think if you were to go to Europe, it would be rare not to do district. Here, it's more of the exception. But the big one that I think is driving it is climate change. I think I don't have to talk about this to this audience. Everybody's very familiar with it, but we have an issue in our hands. And I think we all know that heating is a huge component of it, particularly burning natural gas. And here in Toronto, I think this is from 2017, but about 52% of the GHG emissions within proper Toronto were because of buildings. The next one, which I think is equally as important, is resiliency and in some cases climate adaptation. I was giving a presentation actually about a week and a half ago, and right in the middle of that, I think I was talking about resiliency. I had a power outage in my building and couldn't get back online for 6 hours. And so we're seeing that when you are able to implement some community-based energy requirements and not rely necessarily on the provincial grid, there's a huge opportunity to be more resilient. And this goes to everything from being able to have secondary fuels to back up power, to in some cases a microgrid and CHP, and a variety of other things. And so the resiliency and climate adaptation is really driving the need for district energy. And then the last one, which I think goes hand in hand with the other two, is affordability. What we find is that as you scale up, you're able to have a lower levelized cost of energy. And what I mean by levelized cost of energy, this is the way that we look at it and most utilities would look at it, is not the operating cost and not the capital cost, but the combined total cost over the total energy delivered. And what we find is that as the scale goes up and as the density goes up and as the carbon or low carbon capacity goes up, the levelized cost of energy significantly reduces when you start going with the neighborhood approach. And it's all kind of complement to one another, because as you are looking towards further decarbonization and low carbon technologies such as geoexchange, and to add resiliency, it becomes expensive, or it can become expensive. And so by centralizing, we're finding that there's a business case here where everybody ends up winning about it, where it's cheaper energy for most people involved, lower space requirements, and we're able to tap into technologies that just may not be suitable or economical at an individual building level. And maybe I'll just pause here, a little bit of irony. I mentioned that when we started our company back in 1968, it was to replace natural gas. So it was fundamentally, it started as a fuel switch. And now we're 50 years ahead. It's in Vancouver, one of the greenest cities in the world. We cannot connect new customers to it. We will not meet the City of Vancouver bylaws. So it's an existential project for us to decarbonize. And we're actually working with the federal government as well to not just provide low carbon capacity for new customers, but to decarbonize existing customers. And so we actually have the potential, and we're very optimistic this will be coming forward in the next year to 2 years, that we can do one central fuel switch and actually decarbonize 200 plus buildings all in one project. And if you were to look at the cost of retrofitting those buildings individually, it would be through the roof. And so we started as a fuel switch 50 years later, we're fuel switching again, and we'll see what happens in the next 50 years. So moving on to modern district energy system. The next slide I'll show is a little bit dense. The person who reviewed my slides told me I shouldn't show it, but I will anyways. I think it speaks a lot of things. This was actually taken from a UN report, and this is the evolution of district energy systems back all the way from the 1880s, although technically the first systems were back in the Roman times. And it doesn't really matter the individual technologies that we're looking at, but the two trends that I think are really important to notice here. One is that as we're modernizing district energy systems and getting to third, fourth generations, and there are some fifth generation systems which aren't shown here, there is a very common and necessary pattern of reducing the temperatures of your heat transfer medium. And just referring back to Jenny's slide, it actually goes back to being able to work with heat pumps to a big degree. Heat pumps have a hard time producing very hot water, and they're inefficient when they do so, and they can't produce steam, or at least the ones I've seen haven't. And so we want to have lower temperature distribution to be able to marry up with heat pump technologies, which then can unlock everything from sewer heat recovery to geoexchange to air source heat pumps to data center heat recovery and a handful of other things. But the other trend that we're seeing is an integration of multiple technologies. And this is, as you get up in scale, you see this more and more. But there's a real benefit in this because there's different technologies that will have benefits among different areas of the criteria. And what I mean by that is if you're, get into Oak Ridge, which is a case study from our side, but if you're looking to do a large project and decarbonize, geoexchange is probably a very good option. And it works really, really well for base load and for some other loads, but it may not be the most economical thing to size for the hottest hour of the year or coldest hour of the year. And so finding technologies that can balance OpEx and CapEx ends up being very important. But more importantly than that, what we're seeing is a trend towards integrating electromechanical systems. And so I'll talk about this a little bit more in the next few slides, but we used to see a pattern of saying, well, it's going to be sort of a high temperature combustion based system, whether that's just boilers or that's CHP or something like that, or it's going to be a low carbon electrified type system with heat pumps. And we're actually starting to see that these things are combining, where you might have, at the right size, you might have a central plant with a CHP machine that's powering a microgrid potentially, and also powering heat pumps, which are then trying to get those great efficiencies that Jenny was talking about. And the broader you go with this, particularly as you start connecting not just at the block scale, but the city scale, you're really able to leverage a whole bunch of different technological approaches that can also leverage different primary fuel sources to strike a really good balance of both cost, sustainability, and resiliency. And so that is the trend we're seeing. And I would say most of the projects that we're focused on today are in that third or fourth generation category. And it's becoming more exciting to get into this business because of that reason. And so just before I jump into kind of a couple case studies and some of the rationale as to why or why not we decided to go with certain systems, scale really matters. And there's a lot of little writing there that might be hard to read, and that's okay, but I do think we have to have context in terms of how big are we looking at in terms of the decisions we're making. And so if we start first at the provincial level, that's not really a district energy conversation, but it's important to understand what's happening there, because if we are going to look at electrification as a pathway to decarbonize our heating, we have to make sure that there's a couple things happening with our grid. First is that we have a low carbon grid, or a grid that does not have a whole lot of gas generation on it. And that's really important for today, and that's where you would be looking at things like your average emissions. But it's really important, and I think an often overlooked piece of it, that marginal emissions are equally as important, because what it's saying is every additional kilowatt you put into the grid, you're going to have some peaking generator turn on. And if that's a combined gas cycle gas plant, then we really want to know from an environmental perspective what that marginal emissions rate is. And unfortunately, most carbon accounting protocols don't look at marginal emissions. I know TAF, the Atmospheric Fund, has come out with a really good white paper on this, and I believe that Bob and Vito and Akil will be talking a little bit about that as well. But I do think it's an under talked about topic. The other piece why the provincial is quite important is because we are seeing more and more electromechanical systems where we're producing heating, but we're also producing electricity. And so having the ability to sell that electricity to the grid and having more distributed energy resources really helps the business cases for district energy. And if we're seeing more of these systems evolve, being able to put in certain things like CHP or bioenergy CHP in some cases, and get the heating for district heating, but then have the electricity go to the grid, you can really help the economics of it, and also provide some services for the grid as well. Then moving down into the city scale. And so here, I would be talking kind of about 50 to 100 different buildings, that kind of thing, though it can go up to tens of thousands like you would see in areas like Copenhagen. And here you typically have a couple options that really work well, and it's a combination of bioenergy or electrification. That's typically what we're seeing. And this is where it really works well at this scale. There's a lot more things that can be unlocked when you're looking at projects that are going to be serving 10, 20, 30 million square feet of real estate that you may not be able to do at the 1, 2, or 3 million square feet of real estate, and it's very difficult to do at the individual building level. And so at these levels is where we do see a big opportunity for CHP, for bioenergy, and for a combination of electrification technologies such as sewer heat recovery or geoexchange as well, things of that nature. And then when we move down to the block scale, or what's typically referred to as nodes, that's when we're talking about a development that might have 5 buildings, that it might make sense there to connect or to build a brand new district energy system there. At those scales, it really depends what happens, but it's a little bit difficult. It's more difficult to integrate various technologies as we get smaller, but we're still seeing the same kind of opportunities with respect to looking at bioenergy as a source, and whether that's biogas or biomass or some combination of that, or looking at electrification options, and in some cases microgrids as well. But what we've seen both in British Columbia and in Ontario is that in most cases, the lowest cost for low carbon energy ends up being geothermal. And now I do want to make a distinction. That's not necessarily, or at least in our findings, not the lowest cost of energy, but when you're looking at ways to decarbonize, that is one of the technologies that time and time again forms a component of what we're doing. We do find that sewer heat recovery, ocean or lake exchange can be quite viable, but they're a little bit opportunistic depending on if you happen to have a big deep lake beside you or an ocean, or if you have a big sanitary main coming right through your site. But that's typically where we end up seeing these projects, and then they'll typically also be complemented with some degree of more conventional technologies, such as conventional natural gas boilers or chillers or cooling towers. And the little schematic there to the left that you see, that's actually, I pulled that from a UN report on district energy in cities. And it actually shows the nodal growth to district energy, which is quite common. What you'll see is you start with these block scale nodes that will be built for 4, 5, 6, 7 buildings as part of a master plan development. And then you might have one a few blocks down and a few blocks down, but over time, as the district energy system matures, it really becomes an interconnected citywide system. And so it's a little bit cyclical that what we talk about city scale, sometimes you start off with a city scale project, such as the N-Wave system that serves Toronto or our system that serves Vancouver. But sometimes you build this up over time based on individual nodes, which is a very common theme that's happening out in Europe. From a policy piece, I think I put way too many words on paper here, but I'll try to get my thoughts out. And this is where maybe I disagree a little bit with some of what was presented earlier. What we're finding at scale, we are still finding that natural gas is cheap, too cheap. And I say that not that it's necessarily a bad thing, but there's still a spark spread that's about 3 to 6 in times of the dollar per megawatt hour. And while we can certainly get higher efficiencies in heat pumps, such as 400%, if we have a spark spread of 5 times and our COP is only 4, we might still have a delta. And when we're still looking at this from a levelized perspective, it can become a bit more challenging. And so when I say policy matters, it's gas is still very cheap, and on its own economic merit, we're finding that in at least British Columbia and Ontario, we need policy to support decarbonization. And what we're seeing is that there's policy that happens at the federal level, at the provincial level, and at the municipal level. Typically, municipalities are the ones who are leading the policy piece, though there's some troubles there. But to give some of the examples that really support a low carbon system instead of just a gas system or natural gas boiler type system, at the federal level, there's obviously the carbon tax, or the fancy name for that, Greenhouse Gas Polluting Pricing Act, which is currently at 20 tons and will be $50 per ton by 2022. But in a lot of cases, to really compete. And then the other standard that I'm quite excited about is the Clean Fuel Standard Act, which is very complementary, but quite the opposite, which actually allows you to generate carbon credits that can be generated and sold in the market. And this is really helpful because for a company like ours, if we can decarbonize at a lower cost in, say, Vancouver, because we have 50 years of infrastructure there, we can do that, decarbonize there, and then sell credits somewhere else where it might be more expensive to decarbonize, and it really propels the decarbonization agenda. When we go down to a provincial level, we actually haven't seen too many provincial standards that support low carbon thermal energy. And when I say that, I don't say that necessarily from a district approach. I say that from a sort of agnostic approach of decarbonizing a fuel supply. The only real provincial standard that we've seen have a strong leadership towards energy is the BC Energy Step Code, which is essentially a stepped approach to achieve net zero ready buildings by 2030. It's developed by the province, but implemented by the municipalities. Though it is one of the criticisms of the standard, and it's expected to change the next iteration, is that it's actually completely silent on carbon. And as a standard that's intended to help decarbonize, it's somewhat interesting that it talks about TEDIs and talks about EYs, but it does not talk about greenhouse gas intensities. And the picture you see on the bottom right is actually a really interesting little schematic that was done by Metro Vancouver, who's a quasi-governmental organization. And they just wanted to show a typical house, what would happen at step 1, step 3, and step 5 if it was conventional natural gas heating compared to a fuel switch. And it really, to me, tells a big story that you can't talk about decarbonizing without talking about your fuel supply. That standard is really based on an envelope and demand side reduction, but I like to say the atmosphere is indiscriminate. I think we should be too. So it'll be interesting to see what happens in the coming years. But as we get down to a municipal level, some of the standards that are really making an influence in how we design and size and run our performas and ultimately get lower carbon type of thermal energy infrastructure. The two leading standards that I've seen in Canada right now are the Toronto Green Standard, which I'm sure everybody here is quite familiar with. But then the one that's even more aggressive is the Vancouver Zero Emissions Building Plan, which essentially says all new buildings have to be GHG neutral by 2025, except for high rises by 2030. And what's interesting about the Vancouver standard is that they actually provide a pathway there with a couple options. And they say, first and foremost, we would like to see you connect to a low carbon district energy system. And if you can then show that the tons per megawatt hour are below a certain threshold, you check the box. Then the second pathway is, if that's not there, then it will be a demand side pathway where you're really focusing on high performance envelopes. And that actually is very helpful, I find, because it gives developers, architects, engineers, utility providers a little bit of flexibility in terms of how you reach net zero or how you decarbonize your buildings. And I didn't put it on here, but a very similar standard out there is the city of Burnaby, which is beside Vancouver. They follow the step code, but one of the policies they've come out with and said, look, At this year, you need to be step code 2 or step code 3, but if you can show that your GHGI is lower than 6 kilograms per meter squared per year based on a low carbon fuel supply, then we'll actually let you relax that step code. And the actual envelope implications on that can be tens of millions of dollars for large developments. So moving on to a couple case studies, I'm just checking the time. I've got about 5 minutes left. So we'll first go all the way down to Vancouver and show our Ridge Redevelopment. So this is a project that we currently have right in the middle of development, and it will be about 5 million square feet of real estate, 14 towers, 2,600 homes. And our district energy system will be roughly 30 megawatts of district heating and district cooling. Our system is largely a geoexchange field. That's the base load for the low carbon. And we're also implementing wastewater heat recovery. But one of the surprises to us is that electric boilers actually had a really good place to play here because of the very low capex but very high opex. It was a really good way to take care of peaks without hurting our carbon targets. And one of the biggest things that we're really pushing here is being able to move energy around the campus through heat recovery chillers. And so before we even touch the geoexchange field or the wastewater heat recovery or electric boilers, we first want to make sure that if any building has a cooling demand, we can capture that waste heat and send it to the next building. And to give this in a little bit of context, the carbon targets for this are 6 kilograms of CO2 per meter squared per year. That is equivalent to tier 4 of version 3 of the TGS. So it's fairly aggressive that way. And so this is, I think, the largest low carbon district energy system being developed in Canada today. And we're expecting that in the next couple of years we'll be up and running and be selling. Obviously, it's a multi-phase project at the scale, but we're hoping that we'll be up and running in the next few years and use this as a case study once we can actually start finding out the operations and not just looking at our performers and our energy models. For context about the equivalent of 4,600 cars off the road compared to heating with high efficiency gas boilers. And excuse me. And then the plan here is just similar to the node expansion to growth. We're looking at expanding outside of this master plan and then developing new nodal capacity to hopefully have this not just be at the block scale, but really grow this into a proper, mature district energy system that covers the district scale or the city scale. Skipping all the way out east, the second case study I want to talk about, and maybe case study is a loose term. There's certain numbers we can't share due to confidentiality, but it's our first project here in Toronto, and that's Smurfit Village. And so if anybody's familiar with it, it's on the corner of Bloor and Bathurst. And this is just under 1 million square feet of purpose-built rental and some affordable housing. And it's about 5 high-rises. This project was interesting. It was actually, we did hit version 2, tier 2 of the TGS. And part of our system here is actually a CHP with microgrid and the solar array. We provide district heating, cooling, and electricity as well as emergency power. And what we found here is that the CHP and the microgrid coupled with a little bit of a GA play in terms of how we can try to avoid the global adjustments, that made this project economical. Before we put that CHP machine in, we were finding we were having a tough time being competitive with market. And so we're quite excited about this one because it's the first time we've taken an approach to the microgrid. And essentially the way that this works is we do purchase some electricity from Toronto Hydro, but we will supplement that with on-site plants, and we have sized our CHP for the base load heating. We get whatever electricity we can from that, supplement that with more conventional technologies, distribute the heating through that mechanism, complement it with the solar array, and then we actually are providing emergency power to the entire development through our natural gas generators. And those are there for backup. They're also being used for GA busting. And between the electricity play and the thermal play, we're able to come out with very good performers that actually made the market rates quite competitive. That I think without that CHP enabling it, we would not have been able to do it. One of the challenges, and I'm quite looking forward to the next presentation, is the carbon accounting on this. We were able to comply with tier 2, version 2 of the TGS. The way that carbon is accounted for in the current protocol, we would not comply with version 3, tier 2. And I think if marginal emissions are looked at, it might be a little bit of a different story, but there was a little bit of it's not a low carbon project per the definition, But what we are seeing, what we're hoping to do is we expand this, because this again is one of our nodes, and we're hoping to turn this into a proper city scale system, is actually use that CHP to start driving heat pump technology. And so then we can really leverage that integrated system and use both electromechanical type of generation. And that would be more towards that 4th, 5th generation type of district energy system. And with that, I think I will leave it there and let the next presentation go on. Thank you everybody for paying attention. Look forward to questions at the end of this.
Okay, thank you, Diego. That was a fascinating presentation. Okay, so our final presentation of the evening will be given by Bob Bache, who's a founder of Sustainable Buildings Canada, and Vito Mike Casola and Akil Zaidi. Now, this group has put together a report entitled, this is a bit of a mouthful, I'll be honest, fellas, Combined Heat and Power System for New Part 3 Multifamily Residential Building Designed to Meet SB 10, Division 3, Chapter 1, Emissions Requirements, Final Report for Municipal Building Officials. So without further ado, I will pass this over to Bob, who will lead the discussion, and Vito and Akil will be providing support through this.
Thank you, Adam. This project was driven by what would appear to be a very simple change in Supplementary Standard SB 10, but which in fact had significant impacts, especially on combined heat and power. In 2014, the 2014 edition of SB 10, the concept of determining emissions for the proposed design and the reference building was introduced, but it was based on the marginal emissions for the Ontario electricity grid. In 2017, in Division 3 of SB 10, that factor dropped to 1/8 and was apparently based on average emissions. Though the emissions figures came from the independent electricity system operator, the Building and Development branch of the Ministry of Municipal Affairs and Housing simply requested those numbers. However, it just simply threw out CHP systems in buildings effectively. So we set about to demonstrate that in fact, this was not accurate nor reasonable. And the way we did it, if I can go to the next slide, Adam, is to develop a report which addressed a simple statement that was also in SB 10 2017 Division 3. And what we've prepared is a report that can be submitted to a municipality along with a Part 3 MURB project that has a CHP unit. As you mentioned, Diego, and I will mention, in Ontario as in other jurisdictions, the drafting, the preparation of the building code is done by the Building and Development branch, but the interpretation of the building code is done by the municipality, and in particular the chief building official. So what we have attempted to do is to provide a report that will resolve this issue and permit the chief building official to accept that CHP does meet the emissions calculations. So next slide. The note that permitted us to do this is note 5 to Division 3, Chapter 1, Table 1.1.2.2, which is the table that includes the emissions factors for the grid and for natural gas. And it states that this table is not comprehensive or exhaustive and not necessarily representative of every energy source that may be encountered in a project. Other factors may be used on a case-by-case basis with appropriate methodological justification. So next slide. The methodological justification is what the report provides. And the way we set out to do this was to firstly take the information from the hourly energy model for an archetype mid-rise MURB, which was provided by EQ Building Performance, to take hourly electricity grid emissions that were developed by Power Advisory LLC, and they provided 11 years worth, and the hourly CHP model that has been developed by and managed by PowerGen SIS, which is Vito Casolo. And so the first two steps, the data was provided, and the third step was to take the CHP model and combine the other hourly data and the operation, which it simulates very well, of the CHP unit. And Vito modified it so that it would develop the CO2 equivalent emissions for both the proposed design with CHP and the reference building without CHP. And a complete set of CHP simulations were undertaken for each of the, yes, I said 10 years, 21 years of electricity grid emissions. Next slide. The archetype building is a mid-rise. It's an 8-story building with 1 story of retail, 2 levels of underground parking, as you can see, about 101,000 square feet. And I think the EQ Building Performance probably has the most experience of any modeling company in energy modeling of MURBs, and because their roots were with Tridel, if we go back far enough. Next slide. The Power Advisory did do hourly simulations of emissions. They started with 2014 actual emissions and 2015 and 2016, and then they set to work to project these out for the 21 years. And what you're seeing is a table that was built up by season and time of use period from the hourly emissions. So this is just intended to show what we would have if we took all the hourly emissions and put them into the seasons and the on-peak, mid-peak, and off-peak periods set up as billing in our electricity system. The next slide. So this is a sample of the results for 2020, and it's set up by Vito so that the CHP model, the CHP unit, provides 100% of space heating and a range of surface water heating loads. Now, the column that is most significant is column 12, because that shows the difference between the emissions for the reference building and the emissions for the proposed design. And in every case, the emissions in column 12 are negative. So the proposed design generated less emissions than the reference building. The highlighted row is simply for 2020 and represents one of the simulations that was included in the complete report from PowerGen Sys, and the complete reports of all three of the providers of the hourly data are found in the report that goes to the building official. Next slide. So this is pretty much what I just said, but the key point is that in every case, the emissions from the reference building are higher than those for the proposed design for every one of the 146 simulations undertaken by PowerGen Sys. We did limit it to internal combustion engines simply because the balance of heat from IC engine CHP units worked better in the application that we were considering. And I should add that we chose only to deal with MURBs because their surface water heating load is 12 months a year. So there was a good place still in the summer to be able to use the waste heat from the internal combustion engine. And the last slide, if I may. So the conclusions that we drew from the study were that CHP units in MURBs will always have lower emissions than those without, provided the heat from the CHP is used for either space heating or surface water heating or both within the MURB when the CHP unit is operating to generate electricity. And this is borne out by all the simulations that were done. And we raised the issue and also included a recommendation that it is much more complex to determine emissions than simply to take either a marginal or average or any other single number for grid emissions in Ontario. And so we have in the recommendations, which I haven't, sorry, I do have recommendations. So to the next slide. We believe that municipal building officials should accept this report as validating that a building permit application for a Part 3 MURB with a CHP unit as meeting Division SB 10 Division 3 Chapter 1 CO2e emissions. We think that we have demonstrated without question that in every case this will be true. And then a recommendation to the IESO that they should come up with a better method of, and a more accurate method of determining whether the CO2 emissions from the proposed design will be equal to or lower than those for the reference building. And I do not know what the method will be, but they need to have a better method than what wound up in SB 10 2017. Thank you.
Okay, thank you, Bob. So before we get to the Q&A, I wonder if maybe Akil and Vito would like an opportunity to comment on the report.
I think Bob has summarized it pretty well. There was just one comment, I think in one of the slides, it showed that it was 100% space heating. Actually, in the table, you'll notice that it did say it was 100% domestic hot water. So just so that there's no confusion, that one particular study that was example summary I think it was number 5, and all of them basically were for 100% domestic hot water usage, and then varying degrees of space heating usage. So that's the only thing that I can point out. But otherwise, I think Bob did a good job summarizing the study and the results of the study.
Okay.
Thank you, Vito. I mean, thank you for your correction.
Yeah, no problem. Just don't want people to be confused.
Yeah, so this is Akil from Enbridge Gas. I just want to add one comment about the CHP and the GHG. I mean, that had been a contentious issue, at least as far as I have been involved. I mean, CHG, it was not an issue until about 4 or 5 years ago. And it is the issue is not resolved. And the basis of the analysis is based on what is called site versus source. And in the US, they have a very well-established methodology by EPA, which defines that how these GHG emission savings should be calculated from a CHP system using site versus source methodology. So in this approach, that's the approach which was used, that you take into account the site energy, and then you look at also the source energy as well. And the moment you look at the source energy and you look at the incremental or positive or negative incremental or reduction, you got to look at, then you don't look at the site, you look at the source, because when you put a CHP in a building, it is reducing the draw from the grid. And which is no different than doing any other CDM measures. And so if it is reducing draw from the grid, the moment we say we are reducing draw from the electric grid, that means we are talking about the source energy. So what we have been saying, and I have given presentation at various conferences, at the NRCan Energy Summit and a few others, that the moment you look at the electrical grid, you have to then look at the gas grid. Then you just cannot look at the gas consumption on site. Then you have to see what the impact it is going to have on the gas consumption on the gas fire plants. And the moment you do that, then you have to start looking at the marginal emission factors. And then you have to start looking at the whole generation mix and the emission factor and all that. So that's where we engaged Power Advisory, who is considered as probably the most expert in the field. They know how the grid works. That's their key business. And independently, they did hour-by-hour analysis using the IESO LTAP, Long-Term Energy Plan. And they looked at hour-by-hour analysis for the next 20 years. And that's how they developed those factors. And they developed a model, which is a very strong model, which is and all that is available in the report as an appendix, which has a very strong correlation, which is the residual demand and the fossil fuel generation. So if we look at, when you look at, I think I just want to make one more point, which I think most of the audience, they know that definitely, Ontario grid is very clean. And, but at the same time, we also know that our installed capacity for gas generation is 1/3. It is actually as much as nuclear and more than hydro. So, and there is a reason that we have that 10,000 megawatt of gas generation sitting there. So we just cannot ignore the fact that the impact of CHP, if you reduce draw from the grid, it will have an impact on the gas-fired generation. The other thing which a lot of time, what has gone into actually the same SB10 table is those numbers are based on the historical or what is today or what was, let's say, 2018 or 19 or 17. Anything which gets built, we have to look in the future. We have to see how the grid is going to change going forward. And if you look at with the Pickering shutdown and the refurbishment of all the gas-fired, the refurbishments of the nuclear fleet, we know that the gas plants are going to run way more the way they are running today. So the overall emissions from the grid are going to go up. And even based on the latest annual power outlook, which was published by ISO, it is predicting that our emissions from the overall emissions from the grid, even on the average basis, is going to more than triple. So we just need to take all these things into consideration when we look at the impact of CHP on the reduction of GHG emissions.
Okay, thank you for those comments, Akil.
You're welcome.
We have a few questions already as we move into the Q&A portion of our webinar. If any of our attendees have any questions, please write them out into the question box on the webcam or the webinar portal, and I will ask them for you. So we're going to start with some questions for geothermal. So some questions really directed at Jenny and Michael, but there's a lot of expertise on the panel today. So if anyone feels like jumping in, please feel free. So we'll start off with a technical question about geothermal. What is the expected useful lifespan of a geothermal system or a geoexchange system? And what would be the replacement costs that you need to consider after the wells or the well bores are dug? And so I guess the balance of system replacement costs.
Yeah, thank you for the question. My understanding, and we could double check the ASHRAE data, but the wells themselves have well over a 30-year life cycle. Depending on where you draw the end line or the boundary of the geothermal system, I would say the most vulnerable piece is the heat pump that's exchanging between the building and the loop itself. And heat pumps, I don't know, Diego, you probably know this better offhand than I do, but heat pumps are what, 12 years or so in terms of life cycle?
Yeah, that's about right. Looking at the ASHRAE median life, it goes from 12 to 20 depending on the size. If it's distributed heat pump, if it's central heat pump, that's in the ballpark.
Okay, thank you. Sorry. Okay, so a similar question, a related question, is about the effectiveness of geothermal systems in northern climates. So this ties into another question related about how to avoid the backup or top-up energy source. So the seasonal imbalance, is this particularly challenging in northern climates?
Well, I think that depending on the type of system, so in a vertical well system, you're digging deep enough at 500 feet or so that you're getting a consistent ground temperature anyhow. So it's less about the temperature in the ground. In terms of the building loads and what would likely be almost entirely heating dominant, I'm not sure, depending on the northern community, if there would be any cooling load that would present a challenge. And this is where I think Diego had highlighted this well when looking at community energy systems, and it is particularly relevant in the sizing and the economic aspects of geothermal. But without a balance, it doesn't probably make sense. I welcome others' thoughts because you're probably end up being redundant. Yeah, go ahead, Diego.
Yeah, it's funny. It's a funny question because we just went through this. We're working with the university out in the west, which is not necessarily northern climate, but it's minus 35 type of design day temperatures, and it's a pure retrofit. So we're looking at decarbonizing 100% of their buildings, getting them to net zero by 2030. And unfortunately, one of the issues we found is that they were purely heating dominant because they had very little people in the summertime. And just the temperature conditions, there was not residential where you have big domestic heating loads. It was very, very heating dominant. And so we were working with the geothermal engineering contractor out in the west, and they said, look, we can design a field that can handle those imbalances, because as the field drifts over time, it kind of becomes asymptotic in terms of how much it's going to saturate. but that means we have to really oversize that field. And when we ran the numbers, that one-way balance really killed the business case for it and got ruled off pretty quick. So it was technically possible, but financially uneconomical. And maybe I'll just clarify, I'm not a geothermal expert or engineer, but that was the one case study we were looking at in the web.
Okay, thank you. So this question just came in that's sort of related. Is it, if I'm reading it right, has the geothermal system ever been discharged? So is it possible to, if I'm understanding the question correctly, is it possible to discharge the energy if you get to imbalance? Is there a way to discharge the thermal energy to somewhere outside of the system?
I should have put full disclosure that I am an architect and not an engineer at all, but I think it would depend on how the system is set up. If there was a loop, and many in the district system, there would be many ways of balancing out. But within a particular building, I don't know. I think it would depend entirely on what the loop is sized to. Happy to default to my engineer friend Diego if you have any other thoughts.
I can address that, or I can try to. I'm an engineer.
Please, yeah.
One way to do that, that's Vito speaking. One way to do that is to have cooling towers in the building, but then that defeats the whole purpose of having geothermal. But the cooling towers can be sized to try, for the imbalance rather than the heat load. The cooling load, the summer cooling load. That's one way to reject the heat.
Yeah,
do you agree with that?
I do. I was actually just going to say there's a couple ways that we've done this in the past where we've looked at it. One is cooling towers, which can be used to do that. If you have to charge it, you can do that with solar PV, or in some cases cooling towers as well. I don't necessarily agree that the whole point of geothermal is to avoid cooling towers, because on a district scale system, what you'll typically find is that you size your geo based on your carbon targets, but it might still be more economical to have cooling towers for the very hot days. But in terms of answering that question, I do fully agree with that.
Yeah, okay.
I guess the other thought too is in an open loop system, there would be more flexibility depending on where you're rejecting the heat to. If that could accept a higher load, I would think that would be another option.
Okay, I hope that answers the question. It certainly gave me some clarity on it. So Diego, we have a question about district energy, about scale. You talked a lot about scale, and so we have a couple questions that relate to that. One is the scale of the plant itself. How much space as a percentage, I suppose, of the building or the site would a central utility plant occupy? And I'll let you answer that, and then I'll ask you the other scale question.
Sure. And so in terms of scale or how much space it occupies, if we're looking at say a node for master plan development, what we'll typically find is that we're about 25% smaller than what would be the otherwise individual boiler and chiller plants or penthouses. And in terms of the actual, as a percent, I'm just doing some quick math right now. And it is very small percent. It's yeah, maybe I won't give the number because it varies a little bit by plant, but it is about 20. Typically, we'll see 10 to 20% lower space, if not more, than distributed plants. And actually, I can probably circle back and answer that question in a few minutes. I just want to look at a couple of benchmark stats that we have.
That would be 20% lower when you combine all the distributed plants and you have your total square footage for the combined distributed plants versus the one central plant, correct?
That is correct, yeah. So if we're looking just as an example, let's say Ridge Village, if we were looking at having an individual boiler and chiller plant at every single building, when you look at the aggregate area of that compared to the aggregate area of centralizing, you're typically seeing about 20% lower, and in some cases more.
What about with respect to emergency power for some of these buildings, being that they're high rises, code would require them to have emergency power generators? Has there any thought been given to, you know, combined heat and emergency power, which is a new concept that's been proven? Toronto Community Housing has put in their Region Park redevelopment. They have a community energy center, which does include a 5 megawatt cogeneration system, which also acts as their emergency power for numerous buildings that no longer require to have on-site emergency power systems. So they use those systems to generate electricity. The central plant becomes the central, you know, central cooling, central heating, and also central emergency power for the various high-rise buildings.
Yeah, you know what, that's we haven't done that, but that's fantastic if it's going that way. The only time we've actually taken a stab at the electrical side of this has been Ridge Village with the microgrid, and we have natural gas generators there for the emergency power that serve both our plant and the buildings for life safety, and then CHP for baseload. I don't think we looked at going with just full CHP and avoiding the generators altogether. But I'm very happy to hear that's happening, because that's certainly something of interest.
Yeah, and you're avoiding the cost of having emergency power generators at each facility, each of which has to be tested under the codes, you know, to ensure that they will run when the power fails. Now you have only one central plant that has a central power generation facility that can run as a cogeneration system when there is no power failure, when everything's normal. And then you also have the ability to run, you know, and provide limited and emergency power to the various buildings within the complex that are served by your community energy system.
Yeah, and I would say from a pragmatic perspective, just thinking back to a MURBs example, if we could have one machine that takes the purpose of two, that, I mean, certainly that makes a lot of sense. The only gap I see there, and we haven't ran the economics, we wouldn't know, but there we have a CHP that makes sense to be sized for base load, whereas the generators are sized for significantly more. And so there's a bit of a scale difference there. But if it was economical to just get rid of the generators and do it that way, I think that's a really good idea. You know, one of the challenges we've had as well, and I'll share this is obviously very specific to provinces, but in Ontario, one of the challenges we have with microgrids is a regulatory one, that as soon as we want to cross a public road or a property line, we essentially unlock a whole bunch of regulatory burdens to become a proper distributor and some other things. So we've left it at that block scale level as well. So as we do more microgrids, I might give you a call and try to see if you can help us out finding some of these solutions.
In the case of Toronto Community Housing, most of that was a development. The Region Park redevelopment was a combination of private and public buildings, where you had Toronto Community Housing buildings that were owned and operated by Toronto Community Housing, then some were with Daniels, developer. And so it was mixed use buildings. And yeah, they somehow managed to get around some of those hurdles that you mentioned. But in the case of emergency power, they were dedicated lines to each building. So the CHP plant was not so much dedicated for providing power to all the buildings, only emergency power to all those buildings. Yeah.
Interesting.
But there's a lot you can learn just by, you know, speaking to some of the people that have been involved in those projects. But in the early days, that was in the early days, 2006-07, when we first was conceptualized to do this. Eventually, they did pursue it, Toronto Community Housing, and in the end, they did put in a CHP plant. And I believe that's under the Save on Energy program or the CHIPS-Up program. One of those, they're under one of those programs where they're also getting government subsidies for it, for building the project. So, and now we've just done a study that proves that CO2 emissions also are lower in buildings that have a CHP system incorporated. So, kind of promising. It's going in the right direction.
Okay, let's. This is a fascinating conversation. I appreciate all the detail. We're going to try to squeeze in a few more questions if we can. We have a policy question that I'd like to read to you. From a policy standpoint, does it make more sense to incentivize developers owning and operating their own geofields or district energy of any sort, or focusing on reducing costs with third-party managers who would own and operate the equipment?
I'll maybe give my 2 cents, and I see Jenny's face has her 2 opinions. From a policy perspective, I'm really of the opinion that policy has no place in that. To me, policy should be talking about carbon outputs and targets, but how the market gets to that and who pays for what, I think, is the free market conversation. So I actually don't know that policy has a place in terms of how you set up the business structure. I think policy has a place in saying these are the environmental outcomes we need. So that would be my 2 cents, but I'll leave it off to Jenny.
I think it's a fair point. I mean, if the funding comes out, which I think is what the kind of the question is getting at, it as long as it hits either player, it will ultimately improve the overall economics. And I would echo what Diego is saying. I think we need to be firing on all cylinders as code and municipalities choose to move the yardsticks forward. Developers will follow suit. The leading developers will be looking farther ahead of what the steps. The steps codes are quite good in that way, and it's been interesting to see the market respond already to TGS version 3. I can say in the last year, I guess, since it's been out. I'm sure Diego could echo this as well, and many of the other providers, if any are on the call. The conversation has been open because policy has changed to ask for more. But I think, yeah, so I'll leave it there.
And I would agree with Diego. I think that it was well said. There's a place for policy in emissions, but as far as markets, I think part of the problems we have in the electricity market right now with the global adjustment charge and it being as high as it is in everyone's bill, especially in the commercial and the industrial, global adjustment now has gotten to a point where it's almost 80% of everyone's bill, and it's a number that no one knows what it is until the month's over, so it doesn't give people any real sense of what the true cost is until it's there at the month's end. I think part of that problem has come from policy, and there is no real free market anymore. And I think that there's no place. I'm a firm believer that there's no place for policy and trying to subsidize. It's counter for me. I mean, being a CHP in the CHP business, most of the projects I'm working on now are as a direct result of the Save on Energy project and the CHIPS programs that were put in place in the previous government. But at the same time, I'm a firm believer that markets will ultimately dictate which technologies are the best. And I think, as Diego pointed out, policy should go towards things that we want to achieve in terms of environmental benefits in that regard.
Thank you. Bob or Akil, did you have any comments? Oh, sorry, Jenny, go ahead.
I was just going to add in, and this is maybe very obvious to those on the phone, but certainly tools that help enable a huge sector of the residential market, which is the condo developer who has a short-term horizon and business model and doesn't really realize some of the longer-term life cycle benefits of investing in conservation measures. So I think some more guidance, policy, and support around tools like green loans, as an example, is one tool that can be used when there isn't an energy partner available. I think there are some motivators that are needed to really continue to push efficiency from that part of the residential sector.
I just wanted to jump in and answer a question that I was asked before. I pulled up some of our benchmark data. In the last 7 district energy projects we've done, the plant area took up between 0.4% to 0.55% of the total area, total building area.
Okay, and there was a comment about that maybe is a good time to speak to it. Would a district loop supplying 50 to 60 degrees Celsius water have heat pumps at each building for domestic hot water?
No. One answer. No. At 60 degrees Celsius, you can take care of your domestic hot water. So what we're seeing is that in most cases, we're trying to push for 60 degrees Celsius distribution, because there we can hit domestic hot water loads, space heating loads. And if we can design the building side space heating low enough, we can get really good low return temperatures and get good COPs of heat pumps at the central plant. What you'll see is this came out actually so the city of New Westminster out in British Columbia, they put out an expression of interest for a partner, and they were looking for a sewer heat recovery district energy system to get built. There they had a strategy of providing water at around 45 or 50 degrees Celsius, and there you would have needed distributed heat pumps, or one at each building, to lift it up. But at 55 or 60 degrees Celsius, you do not need any kind of heat pump or lifting device at the buildings.
Okay. Perfect clarity on that question. I like it. Okay, we have one question that has been asked that I think was covered a little bit earlier in the thermal balancing, but I'm going to ask it just to be sure. So it's on geothermal. We know that heating is dominant in Canada, which means that thermal energy sent to the ground during cooling season is much less than the thermal energy extracted from the ground during the heating season. These thermal balancing issues will eventually deteriorate the performance of geothermal heat pumps. How will this be dealt with specifically for MURBs?
A good question, and from the engineers that we've worked with on projects in the Ontario climate, we're not anticipating an overcharge locally. Looking at the combined effect of, if say, MURBs located closely together, I can't speak to, but welcome any other thoughts from the panelists.
I've never seen that be an issue, but I'm not a hydrogeologist, so I will not comment on that one.
Okay. So this question is a great question for everyone to weigh in on, I think. It comes up a lot in our Savings by Design program as well, and that is, is there any comparison of geothermal to other highly efficient energy systems such as HRV and ERVs and VRFs? How do they work together? Can they work together, or should they be used separately? And how do you make that determination?
I can start at a building level, and then maybe we scale up. I think that it depends on what the goal of the building is, I think, and how far-reaching the developer is aiming to be. I think there is some inherent additional efficiencies possible by using a VRF and a geothermal system. What we're finding, and Michael and I are working on a condominium/rental project here in Toronto, and interestingly, hot off the press, the capital cost was actually, or maybe it's not that surprising, that the capital cost is cheaper on the VRF system than the geothermal system. But what's really interesting is when, and again, depending on the core business model of the developer or the owner, the life cycle cost is quite substantially better on the geothermal side. So it's a tough question to answer in that it depends who's developing, who's owning the building, and then how far you're looking to go. So yeah, I would just say, again, capitally could be more reasonable to go with a VRF, but again, depending, that would be kind of in line with a TGS Tier 2 equivalent to building. You might get some extra gain in combining the two, but that becomes quite expensive. So it would depend what the core values are of the project.
If Diego doesn't want to speak to CHP, I can speak to CHP, and I've done a particular study for it was for a development that was considering to put in both geothermal and a CHP system, and so I did a study for that. And the result of that study was that within a year, we saturated the ground with too much heat, because the CHP system was putting heat in the winter, and we weren't pulling as much heat out of the ground that we should have been pulling out without a CHP system. And then when the summer came, of course, typically a CHP system is looking for heat loads, can't find them, and so we need to either dump it through a radiator, and if we try to dump it and reject it into the geothermals, then come winter time, you've got a ground that's again saturated, and you're not, again, the CHP system is providing heat for the building, and you're not extracting it out of the ground. So within, I think, 18 months, we found that we were saturated the ground, and it was a situation that just wouldn't correct itself. It's like you've charge your battery, you've overcharged it, and you don't turn on your phone, and then the next day you're charging it again, and you're just continually charging it. You have to drain your battery in order. You have to have a good cycle of storing and then pulling the heat out. So the experience that we had was that the two systems are difficult to try to marry, and so the system was never built that way. But with respect to CHP is a form of high efficiency generation. I know that the geothermal is also very high efficiency. Which one is going to win out, I think, is a question of, I think Diego was mentioning earlier in his discussions about the spark spread, the price of electricity versus the price of natural gas. And you're talking about heat and versus CHP, which is going to generate electricity for a building. It all comes down to a question of life cycle cost for the building in the two different types of technologies. So, and that's a difficult one to sort of pinpoint which one is going to win out.
Yeah, and I might give my 2 cents too, because I see it very, very differently than I think both. I think, to me, at least at the district scale, maybe not so much the building scale, it's really hard to give an answer because it's going to depend on scale quite a bit as well. So if you take that CHP example, I completely agree. If the CHP is large compared to the geofuel, that's not a very good mix. But if, for an example, we're looking at a system that we're going to develop 5 million square feet of real estate, we have to go hit a tier 4 target or something very low. CHP is not by itself going to get us there. It's better than a reference building, but to go hit a 5 kilogram per meter square per year, we have to start looking creatively. And so if let's just take an example, the CHP is sized to provide some top-up heating and to drive the heat pumps, but maybe not necessarily sized to provide the electricity for all the buildings, we could actually see there that the heat that gets put in by the CHP could work quite well with geo, but it's going to depend on the relative scales.
It all depends on how you size it with respect to your system. Yeah. If you try to oversize it and try to meet the heating loads in the winter, and then you don't have the heat loads in the summer, you are going to run into that problem, correct?
Yeah, and exactly. It's going to come down to scale and what you're sizing respective components to. And then with respect to VRFs, I mean, I think I've got a fairly plain answer from a district component. Typically, it's not a good marriage because VRFs are capital intensive. One of the value propositions of district energy is that the capital goes into the generation plants. If you're starting to put that into the buildings, it works technically. It's just I don't think we're going to see a good value proposition. But I would say in a lot of cases, we find that there's competing technologies and complementing technologies. CHP, what we found is one that can be a bit of both with something like geo or something, maybe let's just say with heat pumps in general. So but if you take, let's just give another example, not geo, but if you go look at the Southeast False Creek project in Vancouver that the city has, they're driving big, gigantic heat pumps that are 2 stories high to pull heat out of the sewer and get water at temperatures of around, I think, 80 degrees Celsius or so, or 70 Celsius. It's quite warm. And they also then have a huge natural gas boiler plant. From a capacity perspective, the sanitary heat recovery and the heat pumps are sized for about 1/3 of the peak, maybe a little bit less, and the boilers provide the rest. But from a load hours perspective, the sanitary system covers about 70% of the load. If you want to put a CHP machine in there, you could use the electricity to drive those big giant heat pumps, extract the heat, and then you get rid of your boiler plant. And so that would be a really good example of a complementary technology. So to me, these kind of questions there are no blanket answers and are very, very specific.
I agree. It is very specific to each development, and you have to be creative, and this is why you need good engineers to come up with these niche opportunities, if you want to call them.
We have the benefit of being technologically agnostic, so we get to play around with a bit of everything.
Right.
That's a good thing. So, okay, I think we have time for 2 more questions. So one is we're going to go relatively small scale, and the other one relatively large scale, I hope. So the first is about scale itself. Is there a size of development that it's too small for a district energy system? You talked a lot about Region Park, which is started out relatively small redevelopment, but is aiming quite big, and that's part of their appeal with district energy. But what would you say would be the lower threshold for using a district energy model?
So we actually have some pretty defined answers on this one, at least based on our business. What we find, it depends on scale is a big part of it, but density is the other part, and carbon content is the other part. And so if somebody approaches me and tells me, hey, we're building 5 buildings, 1 million square feet, we want to work with you, are you interested in building a new plant? But we have no carbon targets, we just want to put in natural gas boilers. We wouldn't do that project, not necessarily ideologically, but because we don't think we'll drive enough of a business case there. If that same developer approached us and said, we want to do this project, but we now want to hit TGS tier 2, which requires a carbon intensity of 15 kilograms per meter squared per year, we know that shift in terms of overall capital and some of the other things start putting that business case together for us. And in one project that I will not allude to in too much detail, but other people on this may know it, it's about 500,000 square feet, but it's targeting net zero, and something like that, district energy makes perfect sense because of that low carbon content. So you need to understand those differences. As a blanket statement, I would say anything that's got some decent density and it's over about 1.5 to 2 million square feet of development area, you can probably justify a brand new node for. And if it's a non-profit organization or NGO or a city, even smaller, because they don't have to make a return on their investments in the same way a private company would. But as we're moving towards lower carbon developments, that area is shrinking significantly down to the sub-million square feet area.
Okay. Does anyone else have any comments on that? Okay, we'll lead to our final question, which is a much larger scale, I think. And Diego, you sort of alluded to it in your answer there. One of the big challenges that we're trying to address here is the challenge of low carbon. So with geothermal, geothermal is sort of input agnostic to some extent. The energy comes from somewhere and it uses it in a balancing system. However, CHP typically is running on natural gas. So is there a significant difference between large scale natural gas power plants and smaller scale CHP in carbon output, and how can CHP get to a net zero carbon energy system?
You want to try to answer that one, Diego, or you want?
I'm happy to take the first stab at it, but I know we'll all fall down on this piece and you can pick it up. So it comes down to looking at carbon accounting. And what I mean by that, if you look at a heat pump and let's just say geothermal, hypothetical numbers, let's say you have seasonal COP of 4, and so you know you're putting in 1 kilowatt of electricity for every 4 kilowatts of thermal energy out, then you have to look at what is the carbon constituent of that kilowatt of electricity that you're putting in, or kilowatt hours if you want to look at duration. And then that's where some of the work that the other folks on this panel have been looking at. And without looking all the way back to the generation from the grid out to the output, you can't answer that question. One of the, and two last things I'll maybe say here, one of the challenges is that when we look at something like the TGS, it is a little bit of a false image because it just uses an average emissions factor, which is significantly lower than I think the reality. And so it actually really leans towards electric type solutions of heat pumps, where in reality, if you look at what is the carbon footprint of generating, let's say with a CHP compared to a combined cycle gas plant, the CHP certainly can be more efficient, but understanding it all the way back to where is it being generated from the grid to what's it driving on the heat pump, I can't answer that question because I've not done that carbon accounting. I am not smart enough to understand the Ontario grid, but that's why Akil, Bob, and Vito are here.
Right, and Akil, do you want to give a stab at that based on like the work that we did in our study and what our findings were?
Sure, yeah, very interesting conversation. So I'll be short, respectful of the time. I just will make 2 comments. I think that COP is very important, what you mentioned, Diego. When you look at the combined cycle, just a rule of thumb would be, as long as the COP, I think you mentioned that before, is greater than 2.5, because the average efficiency of gas-fired plants is about 40%. And so that brings you to COP, relative COP about 2.5. As long as your COP is more than 2.5, on the GHG side, you're beneficial not to use grid electricity produced by gas generation. But if your COP drops, then, and it also depends on the type of the season, type of the year. So that's why the table, what you saw with the marginal grid emission factor is very important, because it is not a constant number, it changes. So this correlation is very important. The accounting is very important, and that's where the policy, the discussion we had, I think, is on one hand the policy could be good, on the other hand it could be bad. It all depends, what the policy is for. Right now the policy does not allow, to my knowledge, to do the accounting using site versus source. The way the accounting is, it is based on the site. And unfortunately, which is very unfortunate, that in Ontario there are so many projects which could have brought millions of dollars of investment to Ontario got killed just because of their simple policy that it does not allow that GHG accounting, which would be beneficial. And the last comment is, when we look at the low carbon or net zero and what the fuel source or electrification, one thing which doesn't get looked at is that the assumption is that the gas grid is going to stay the same the way it is today. However, we know that the gas grid is also going to change with time. And when we look at by 2050, probably there may not be any carbon in the grid. So you could still use the existing infrastructure, but instead of having a carbon fuel, which is natural gas, you could have a fuel which is literally no carbon. And that's where the work is going on. And that's the message which sometimes, just gets overlooked, that the assumption is made that the gas is going to stay the same. So if you put something today, it is going to last for another 40 years or 30 years. So one has to look into account a little bit of a life cycle accounting and have to keep into consideration that how the gas grid is going to change. Like right now, we are working on putting renewable natural gas into the grid. We're looking at a lot of work going on in the hydrogen. So in future, the grid is definitely going to look very different. So one has to take all these things into consideration. The beauty of district energy is, I'm a big fan of district energy, have worked a lot in that area, that it allows you to make that fuel switching so easily as compared to making that fuel switches at thousands of buildings. I think that's, I will just stop there.
I think I owe you a beer, Akil. Thanks for helping my business.
Right, and also CHP is always complementary in district energy systems and being, very flexible. When you need more heat, you turn the CHP system on, you get the benefit of the electricity generation, and you add the heat in the system. And when you don't, you turn the CHP system off. So it is flexible, it's dispatchable, and a very good complementary technology for district energy systems that are compatible with.
I just said, it's interesting in this conversation, and I have a question out of this this discussion of the uncertainty of what the emissions will look like on both the electricity grid side and as well as the gas side. And I think Akil rightly pointed out that there's some hope that the emissions associated with what is currently natural gas distribution might go down, but they could also go up significantly as more drastic measures are required to source that fuel. And arguably, you could make the same argument on the electricity side, as I think the conversation has mostly been doing today, of it's, as there is more load on the electricity grid, we'll need to be more creative and look for other sources. And this is actually, I'm redirecting this to you, Bob, and I hope it's a fair question, but for someone who spent so much time in policy and building code, your study, I think, is really needed to help balance out what is an average emission factor. But you can understand why we get to a place of putting an average emission factor in, that it's so difficult. There's so many permutations. So I'm just curious if you have any thoughts, given where we're at today, how should we be looking at emission factors in the code going forward?
Quite honestly, Jenny, I have not attempted to address that, neither in the report or in any other way. I threw the challenge to the IESO because I thought that I mean, how do you increase the emissions by 8 times without any kind of explanation or anything at all? And so something better needs to be done. I do not know what that is going to be.
So Bob, when you say increase the emissions by 8 times, you're saying that previously CHP systems burning natural gas were deemed to produce a certain amount of emissions. Now all of a sudden they're deemed to produce 8 times more than what the electricity grid is producing.
Well, no, it isn't targeted at CHP systems. It is the operators of the electricity grid saying in 2014 that the emissions will be this much based on marginal emissions, and in 2017 saying, oh, it's dropped by 1/8 because it's average emissions. And suddenly CHP went from looking pretty good to looking pretty bad on the emission side.
So it's not that CHP is worse, it's that someone has said and stated that the electricity grid is 8 times cleaner, or
Exactly.
Yeah,
exactly, and
not
clearly
8 times more, 8 times less on the electricity grid. So this is what the CHP now is competing against, is that through whatever policy has been put in place and whatever numbers they've been telling us. And this was the root cause and the root purpose for the report that we undertook, was to develop, a very detailed look at hour by hour what the grid emissions are, and then comparing in each hour if a CHP system is running using those hourly grid emissions and comparing the CHP and the reference building that needs to burn gas to heat its building, to provide its heating loads, and also import electricity versus a building with a CHP system that has on-site distributed generation to meet some of its electricity requirements, and then very efficiently use the heat from the CHP process utilized for the heat loads in the building. And when we do utilize the heat and the CHP system runs efficiently, as Bob pointed out earlier, in almost every scenario, we proved that the building with a CHP system is always going to produce less greenhouse gas emissions than one without.
And the other point I want to make is that it isn't that the approach to determining grid emissions to be used to determine a building project's sustainability, or rather GHG emissions, could apply to any one of a number of other systems providing energy to the building. And so this is where I think it really gets into trouble. And you have, Diego and Jenny and Michael have touched on some of these systems, but there could be others developed in the future. So what we simply said to the IESO is, you got to do better than this, guys.
I think that's an important note for the IESO.
And let me just add one very quick point. I'm not going to comment on grid emissions because that's a topic that I think you could spend a whole career on, and I've spent very, very little time on there. I know a big part of it comes down to carbon accounting protocols. But I just want to throw this out there, that we keep talking about CHP and we keep talking about natural gas. I don't think we should forget that CHP is not just natural gas. If you go look at Europe, bioenergy and biomass CHP is all over the place. And I think that's certainly going to have a part into the equation in Canada. So conversation for another day, but we should keep in mind that there's some very successful countries who decarbonize through bioenergy,
right,
with CHP as well.
Renewable CHP, like landfill gas, wastewater treatment plants, done a number of those, and that's another topic of discussion.
That's a very good point. Okay, unfortunately we're out of time, so we're going to have to wrap up here. Thank you all. Thank you for joining us this evening. And I'd like to thank our presenters, Jenny and Michael, Diego, Bob, Akil, and Vito. Thank you all very much for your research and for presenting your research to us. I'm sure you've generated a lot more questions, and I'm sure these reports will be downloaded substantially. They're very, very compelling and complex topics. And I would say one of the greatest downsides of the webinar is you don't get any applause at the end of any of this. So just applaud yourselves. Thank you for your time. And I hope you all have a wonderful evening. And as soon as we're back able to do presentations like this in person, I hope we all see you out there. And with that,
thanks for organizing.
Yes,
very
thanks for organizing.
Our pleasure.
Night,
All
everybody.
right. Good night,
Thank
everyone.
you very much.
Bye.
Good evening, everyone.
Bye.
Take care.